in fact, that 4/3 pi r cubed looks something like this. Okay, given that data. And so you could have delta S on the right-hand axis, and you'd want a behavior that looks like this. So it shoots down very quickly. So it's 1 over 4/3 pi r cubed, essentially. Does that kind of make some sense? All right, you know, assuming perfectly round cows and all that good stuff. All right, so this is what we're doing here in this context. Does that make sense? Okay, kind of, sort of. All right. It's attempting to connect the linear R to a volumetric based on R. Okay. No, you won't see questions like this on the test. All right, let's just get you thinking about it. All right. And so question 2 shows us this nice hot stage microscope result. So this connects very closely to what we have here for concept test 3, where things were empty and now they've all filled up. All right, all that amorphous space has been chewed up and turned into this. And the question is asking you, sketch the interactions between single crystals from opposing spherulites at the boundary. Include at least some information on the polymer chains themselves. So what did you guys get? Yes?
So I said that basically the chains, they're not full grains, so the chains will be on both sides. They'll be on both grains and like going across the boundaries.
Right.
And everything like that.
So the polymer chains were there first, as I always say, and so the polymer chains will be crossing back and forth. And if you want to think about zooming way in, that's probably a good idea. What else is going on? Is there a comment?
There'll be like some van der Waals bonds between the branches going on of the chains.
Yeah, you could try to draw van der Waals bonding. It can be pretty messy pretty quickly. That's kind of zooming in a little too far, I guess. What else is going on across this interface, though, besides the polymer chains? Yeah? Interdigitization. So let's take advantage of technology here. So we have polymer chains, which we know were there first. So 30,000 feet, we can see that optical effect known as the spherulitic boundary, but polymer chains are ignoring that boundary. All right, they're not cut. All right, nothing happens to them in the process of crystallization. They're still there. Carbon-carbon bonds being very, very strong. And then we also have the fact that, and we'll talk a lot more about this today, that these crystals can cross over as well. All right, so that optical effect we talked about before, the Maltese cross pattern, doesn't cut the crystals either. The crystals can cross over that boundary also. And this is that phenomenon known as interdigitation. No, I can't talk to you right now. Any questions about that? Does that make sense? All right, so this is 2 reasons why these boundaries are very different from grain boundaries. And grain boundaries are a weak point in those structures. With spherulitic boundaries, they're not weak points in the structure. Just like everything else in that structure. Any questions, comments? Make sense?
I have a question, I guess,
Sure.
about the yellow and the blue lines. I mean, I get the polymer chains part.
Huh?
I get just the questions about the yellow and the blue.
Yeah, so the yellow is supposed to be the left-hand spherulite, and the blue is the right-hand spherulite.
It's the
That's
combination of these right here going over the
yeah.
boundaries, right? Is it these, like these right here, going over the boundaries?
I'm not really sure what that is.
Aren't those like the wings of the spherulites?
Well, so the spherulites are made of many thousands or millions of individual crystals, and that's what these 2 colors are trying to show you. So These yellow lines are individual crystals from the left-hand spherulite, and the blue are individual crystals from the right-hand spherulite. I think each one of those crystals is maybe that cartoon you just showed me.
Yeah.
Okay. Yes?
While we're on the subject of tests, can we get the answers for the last midterm posted on Carmen's?
A week ahead of the exam date. I'm sorry, the day before the exam date.
That's a big difference.
Yes, well, I found from experience that if I give you guys the answers right away, people say, oh, yeah, I knew that. And so it's better if people struggle with it for a little while, and then you get the answers the day before. So, yeah.
Can we do like Tuesday possibly, so that Wednesday we could like ask questions, because we'll see you Wednesday, if that makes sense?
Yeah.
Well, I do have office hours on Thursday.
Okay. So like Wednesday
We
night.
don't want to overcrowd.
So 2 days.
What's
It's
that?
going to get crowded in office hours.
And you got me for 2 hours on Zoom. You guys can go for longer than that. And there's also email. I mean, if it's that big a deal, I'll post the answers on Wednesday instead of Thursday.
Thank you.
All right. Okay. Well, this got deviated considerably from what I was going to talk about. So, all right. So make sure your names are on those and pass them forward.
I don't know how to draw this.
That's all right. See you in a second.
Just how they're both going on to either side of the boundary. There will be qualities from either crystals along with each other. This is very hard to
All right. So first off, this is the same experiment, Huxley's microscope experiment, showing the crystallization of polypropylene, as we already talked about before on concept test 3. And this first question asks you to use a simple geometric relationship to sketch the estimated volumetric rate of entropy decrease for the corresponding bulk plastic. So you're given radius as a function of time, and I'm asking you to go from linear to 3D. So what relationship might help you describe that volumetric relationship, assuming perfect spheres and all that good stuff? Anybody? So we have R. All right. You want to go to 3D. R cubed. Okay, that's a start. And what's the rest of it that goes along with R cubed?
4/3.
4/3. 4/3 pi R cubed gives us a volume. All right. We also know that it's going to be a decrease. So as R increases, this volume term is going to drive down the entropy dramatically.
Previous mention, do you think there are things on it that we haven't even begun to cover yet?
Yeah, that's possible. Yes, I have the notes here. Unfortunately, they did not get stapled. They weren't to be stapled. So try to. So you need to get 2 pages. The pages are 2 notes. The notes are 2 pages long. So try to make sure you get those 2 pages. All of them? So today we're going to talk about thermal property characterization, and some of this you guys have probably seen before, hopefully. And we'll start with the simplest technique, which is Tga Thermogravimetric Analysis. You heat something up and it does things. And I guess if you haven't seen this previously, this is sort of how it works. We have our sample sitting over here, and then in a different pan connected to the same balance we have an inert material. And so this can be something like alumina powder, which is a popular one. There's other things that have been used for polymers, but alumina is a good one. And that's designed to do nothing while the sample itself does something in response to being heated up. And the data for a polymer can look like this, which is I guess you can hopefully see this. That's 306 degrees centigrade. And we're looking at some type of polymer that, first off, can show us decomposition onset of an additive. So this can be like a plasticizer or maybe a lubricant, something that's present but not in great quantities. And so that evaporates first out of the system. And the differential analysis shows that it's got a characteristic peak of evaporating out of the system of 324.06 degrees centigrade. And then as time goes by, that kind of finishes up coming out, and then we start to go to the main weight loss, which is this steep dive here. And then in differential form, that also shows up as a peak. We do a lot of differential forms here to discover this information. And then as time goes by, we can see oxidation of some type of additive, and that could be like maybe a metal powder or something. And then what's left behind, which is non-zero, is some type of inorganic filler residue, like talc or clay or something like that. It doesn't evaporate under these conditions, all right? And so this is just showing us the weight loss behavior of these materials as a function of being heated up. And this can be handy in terms of establishing desorption of gases, environmental effects, like you just saw this oxidation behavior going on in these systems. Solvents left over from processing, assuming they're solvents. It's not always true. And then more likely, however, are plasticizers and additive reactions. And so things that are present, and we haven't talked about them yet, but plasticizers, lubricants are typically lower molecular weight compounds. They're not liquids at room temperature, they're solids at room temperature, but we go to high enough temperatures and they start coming out. And you can also have interesting things like additives. Titania is famous for this. We'll talk about titania, why it's there later on. It has the ability to react or catalyze things at elevated temperatures. And so there's a lot going on in these systems that can happen and be detected via thermogravimetric analysis. So that should be pretty clear. The main topic of today's discussion has to do with not looking at weight loss, although weight loss is handy, but differential scanning calorimetry, sometimes called, you might see this elsewhere, DTA, differential thermal analysis, but for polymers we typically talk about DSC. The difference is getting fuzzy. DTA is usually higher temperature than DSC. It's not, there used to be a clear dividing line between them, but it's not so clear anymore. But anyway, DTA is sometimes used, and it essentially means the same thing. And this is very similar in terms of the experimental setup, in which we have our sample again. And so used to be we didn't have one of these in the department. Now we do. You guys probably may have had some exposure to this in lab. Yes? No? Okay, great. Awesome. So, and it's a really nice system too, so I'm glad we bought it. And then this is also compared to some other reference powder that is inside the same furnace, the same atmosphere, the same heating rate, everything exactly the same. And you've got two thermocouples, and that's the heart of the technique. These thermocouples that are measuring changes in our sample versus not changes in alumina or some other inert material. And so it's a relatively simple technique that gives us a lot of useful information. And first off, it just, as it says here, compares changes in temperature versus heating between a sample and some type of inert material. And so what we're showing you here is for a polymer, a couple things. One thing we just talked about last time, which is the glass transition, which we know happens at relatively low temperatures. We can do this for polycaprolactone in our system that we have in the department, so that's nice. This has a relatively low temperature glass transition that's being detected, and this in this context, and I apologize on behalf of the field, they flip this up and down all the time. This is an endothermic transition, meaning that it absorbs heat as a function of temperature. And then what's going to happen in the context of these types of polymers, we then see a crystallization, and we'll talk about this in more detail. This is exothermic, meaning that it liberates heat, and then this follows up with a melting, which, because it's pointed downwards, must also be endothermic, meaning that it absorbs heat as well. All right, so you guys maybe have seen some of this already. I think if you've gotten, I believe the one lab does this. Any questions so far? So what happens as a function of heating? All thermal events are detected. The glass transition, again, if your system can actually see it. Sometimes Tg is below what our unit within the department can actually detect. Tm, which is the melting event, and any decomposition that's happening, and any volatilizations if they are significant enough. So anything that causes the change in temperature of our system is going to be detected by DSC. And so if we volatilize a solvent, that cools the sample off, all right, so we can see that. If we start to decompose the polymer, usually at relatively elevated temperatures, that's going to be typically a kind of a soup of stuff that's all happening all at once, and you'll see a lot of jagged lines associated with that. Can be detected as well. Anything involving chemical reactions, if they are existing, anything that contributes to mass loss is going to be detected also. All right, because the hottest molecules leave first during mass loss, meaning that what's left behind is cooled off. All right. So hopefully this is somewhat familiar to you, and now what we're going to do is talk about how useful this is in terms of helping us understand what goes on in these systems. And the first thing we're going to talk about is polylactic acid, which is a biomedical polymer that you guys don't have to memorize the structure of, among the many things you don't have to memorize the structure of. And this is what we're looking at is we're mixing copolymers with PLLA alone. All right, so PLLA in this context is this first curve, and I'm going to attempt to follow it. And so forgive me if I don't do the best job because my finger is too fat. So this is showing you, trying to nail it down. That's PLLA. Pure polylactic acid. So I'm attempting to show that. Okay, and so PLA by itself has this characteristic behavior. So first off, the other thing I need to do is make sure you understand the setup. So what we're doing is we're taking PLA and we are, as it says here, crystallizing at 130 degrees. Okay? And so that means that in a separate experiment, we take the PLA, we go off, and we let it sit at 130 degrees, and then we cool it off, and then we put it in our DSC. Okay? And what we're also then doing is these other curves involve PLLA blended with copolymers that aren't necessarily PLLA. Same thing's happening. We're going off and isothermally crystallizing at 130 degrees C, and then we take it out of that and we put it in our DSC and heat it back up again. And that's what these curves are. All right, so make darn sure you're aware that when we talk about DSC, we're talking about a separate experiment that feeds into the DSC data. Okay, keep seeing that over and over again. So make sure you realize that there's something else that occurs before we do this analysis. And so what we see as a result of that, first we start with the PLA alone. Whoops. All right, and then we start blending it with, as it says here, increasing copolymer content. And these copolymers are not pure PLA, it's PLA and something else. And you guys should realize that when we do that, we start adding defects in the crystal structure. We're forcing it to incorporate things that aren't PLA or aren't lactic acid. And so what we see in terms of the data is it starts to shift to lower and lower and lower temperatures as we start to add in more and more copolymer. All right, so again, we do a separate experiment, isothermally crystallize 130 degrees C, pull that out, stick it in the DSC, and these are the traces that we get in that DSC experiment.
What's before the DSC usually?
What's that?
What experiment is before the DSC usually?
What's the what for DSC?
What experiment is before the DSC usually?
This furnace treatment, this isothermal crystallization. All right, so we isothermally crystallize at 130, we cool it off to room temperature, we then take it out and carry it over to our DSC and get this data inside the DSC. Okay? And so what we're seeing is, in this first case, it's a melting point more or less of, let's just call it 170, oops, 100, come on, why'd you stop? 172 degrees centigrade, okay, and then we go to these other temperatures, and you can see this first one is more like 160 something, and then this guy is right around 160, and then this is below 160. And so the essential melting point that we're seeing is starting to decrease in this context. All right? And so what that means is we're seeing lower melting temperatures for these increased contents of these copolymers. Any questions about that so far? Yes?
Do you know the same thing as PLLA, or is PLLA the 130 degrees Celsius like difference, or is it just the same?
So it's polylactic acid is the initial curve, that blue curve.
Okay.
And then the green curves are blends of polylactic acid and various copolymers. Does that make sense? They've all seen the same 130 degrees C crystallization treatment, and then they're all thrown into the DSC, and these are the traces that result from that. Does that make sense?
Yeah, I was just talking about the nomenclature of like PLLA versus PLA, which is how the only time I've seen.
Oh, okay. Yes. So there's a, so the double L means it's the levo form of lactic acid. So it's polylevolactic acid, but it's just lactic acid. All right, so you don't need to worry about that here. Any other questions? Yes?
You said that's the melting temperature, so is the graph inverted? That is what melting usually is.
Again, so we flip things around, all right? And so we know that this melting behavior is going to be endothermic, right? So we just flipped it based on the last graph that I showed you. It's one of the really annoying things that they do. They just jump up and down all the time. Good question. Okay, and so what we're doing by adding in this copolymer is we're seeing a decrease in the stability of the polymer crystals, and so the melting point is starting to decrease because we've added in things that don't belong to that crystal structure. And so this is the weirdness of polymers. You know, it's not like a ceramic or a metal where the melting point is always the same. Here we can dramatically vary that melting point. Any questions about that? All right, and so something that's a little more familiar to us is DSC of a polypropylene copolymer. That one we know, but what we're doing is we are looking at isothermal crystallization at 55 and 65 degrees centigrade, and we're looking at these different crystallizations at 55 and 65 degrees centimeters for different amounts of time. Okay? And so again, I'm going to show you the best case. So again, picking blue. So this is 10 minutes. At 55. And this one over here is 16 minutes at 65. All right, does that make sense? Is it hot in here or is it just me? It is hot. All right. Make sure I have to go back to wearing shorts in here. Okay, so the copolymer content is limiting the crystallization that can take place. Again, keep in mind there's a separate experiment that involves this isothermal crystallization at two temperatures of either 55 or 65 degrees C for different amounts of time. Unfortunately, they're not the same amounts of time for each temperature. Okay, so we have this in one case. What we're seeing is a melting temperature of a little less than 100 at 55 degrees centigrade, and in the case of 65 degrees centigrade crystallization, it's over 100. Okay, so why does that happen? Why does different temperatures give us different apparent melting points when we heat it back up again? So think about what we talked about last time, which is undercooling and all that good stuff. What's going on if we let it crystallize at a higher temperature? There's more energy available, right? Okay, so we can get more perfect crystals. We can get thicker crystals when more energy is available. So this relates right back to undercooling or supercooling or whatever term you use. So we give it a higher temperature during the crystallization process, we get more perfect crystals, and then when we put it in the DSC and run this experiment, we see a higher apparent melting point, which reflects the greater thickness, the greater perfection of those crystals. Does that make sense? Man, I have to bring a fan in here. I don't know if opening a door will help or not. Or maybe not. Never mind. These things are supposed to be helping us, right? I'm going to drape myself in a swamp cooler while I talk to you. Okay. Oh, yeah, that feels good. All right. Okay. Again, separate experiments, and we get these results. And what we're looking at is a polypropylene copolymer. And so we have these two differences, and then things get even more complicated. So we have this 55 degrees C experiment, and we have different times at 55 degrees C. So we start with 10, then we go to 16, then we go to 30, then we go to 62, then we go to 122 minutes, sitting there at 55 degrees C centigrade. Okay? And so what we have is a simplest case, and then we start looking at these longer times. And so we have more and more time, basically increased time. And so what we're doing then is we're starting to incorporate lower and lower quality crystals into these systems. And so what that means is we get these different melting events which actually extend down to really low temperatures. So instead of 100 degrees C, we're now seeing this melting behavior at 70 degrees centigrade, for example. All right, and we get more of it as we sit there for longer at 55 degrees C. Okay. So what that means is we are generating a range of crystals with dramatically varying degrees of perfection, and in some cases we get crystals that melt at temperatures as low as 70 degrees. Okay, and this is polypropylene, which has a strict melting point of 160 degrees. And so what we're doing is we're forcing these things to have a lower quality, and thus we get these melting behaviors at temperatures that are very low. And the same thing holds true at 65. Everything's shifted up to slightly higher temperatures as a result of this, but we get the same kind of trend. All right, crappy crystals are formed, and those crappy crystals melt at relatively low temperatures. Does that make sense? Yes.
Don't you also get more perfect crystals?
More what?
Like more of the good crystals?
Yes. Yeah. So yeah, we are getting more good crystals as well, and that's reflected here in the fact that this intensity's gone up a lot of these higher temperatures. But along with those good crystals melting, we're also seeing poor crystals melting. More time, more driving force for nucleation and growth. We get more melting behaviors. Yes?
So does the time refer to the isothermal crystallization, or does it refer to like the DSC?
Yeah, so the time refers to the isothermal crystallization.
Okay.
DSC is the same. So they'll pop it in the DSC, and they will run it at 5 degrees C per minute.
Okay.
And that's the same for all these experiments. It's always 5 degrees C per minute heating up. Okay. So again, make sure you understand that the setup is different than the measurement. Any other questions? All right. Okay, so if that hopefully makes some sense, then we have this issue of variable time of crystallization. So now we have something that's a little more familiar to us. We're looking at polyethylene. And we are crystallizing it at 133 degrees centigrade, and we're doing something called AFM, atomic force microscopy. Are you guys familiar with that technology? No? Okay, some yes, some no. All right, so AFM involves taking a silicon nanoneedle and tapping it on the surface or across the surface of, in this case, a polyethylene film as crystallization is going on. And why that works for us here is the crystals, again, this cheat we have of thinking of the crystals as little rocks inside of the relatively soft amorphous phase around them. And so AFM looks at the resistance to this nanoneedle as it pokes on the surface. And so the nanoneedle can detect the crystals that form because they're harder. And so it sees a different modulus when it taps across the crystal versus when it taps across an amorphous content. All right, so these images are showing you that feedback from the AFM as it taps across the surface. It sounds really crude, but it actually works pretty darn well, especially in this experiment. And this, again, is for polyethylene. And what we're seeing here in this first case, again, it's sitting there at 133 degrees centigrade. And we see these primary crystals that form. All right, and so these are occurring at the highest time and temperature when the most energy is available. All right, so we get thicker. And so those are the most perfect crystals that are forming. And then as time goes by, and unfortunately we don't know how much time has gone by, but we know that B is a later or subsequent version of A, and so we have these crystals that have formed, and if you look closely you can see the crystals in A that are still there in B, but now we're starting to get these smaller, thinner crystals, shorter crystals that are forming as well. All right, does everyone see that? Kind of, sort of, right? And then in C, all right, we're also getting even more crystallization occurring after A and B have formed. Any questions about that? All right. If we did do a DSC experiment, the subsequent crystals will melt at an earlier temperature, they have lower stability, and they're thinner. If we were to do DSC on this.
All these are of like single polymer crystals, correct?
Yeah, well, I mean, everything you see there is at least one polymer crystal. Sometimes it's hard to tell exactly how many there are, but they form these nice straight lines, at least in these films, which is what we're looking at. This is not a 3D experiment. This is a thin film again.
I just meant like this one kind of polymer. There aren't
It is one kind of polymer. Yeah, in this case, you're right. This is all polyethylene. This is not a copolymer. Any other questions? Those are all good questions. You guys need to make sure you understand this in terms of what's DSC, what is the experiment, what is it measuring, and what are the setup conditions that go into that DSC. You need to rock and roll here. So this is showing you, unfortunately, this is what's called BAC8, which is a polymer that seems to only be useful in DSC. It doesn't really actually utility, but it's great for looking at than DSC. And again, we're looking at AFM tapping mode. Primary crystallization is initiated heterogeneously. We all know that at this point. There's no argument there. We have 10 nanometer dirt and crystallization occurs. AFM can see that crystallization occurring, and this is a really nice experiment. We're looking at just a tiny little dot that is our first crystallite forming. And then as time goes by at 20, and this is, by the way, this is 22 degrees centigrade, which is one of the reasons why people like this polymer. It does all this at these ridiculously low temperatures. And so that initial dot forms, and then it starts to grow as time goes by. Whoops. So it gets a little bit larger, and then the more time goes by, and whoops, let me erase that because my fat finger is not doing a good job of this. So we have a polymer crystal here, and it looks like we probably have a second polymer crystal there because it's slightly at an angle to that first one. And then we might even have a third crystal showing up, perhaps, coming off of that first crystal. But everything continues to grow away from that initial point of nucleation. Does that make sense? So we have a growing primary lamella and the development of at least one branch, if not two. All right, so this is, again, crystallization from the melt, and we're monitoring that melt using AFM. And this is kind of the baby steps of spherulites starting up from some heterogeneity, and these dominant lamella set up the initial structure. And then we go to, again, the same BAC8 at 22 degrees. We start with some initial nucleation point, and we start to see, rather more than just one, we start to see multiples. And if we zoom in on this final result at 2 microns, we have, you know, a good 20 or 30 individual lamellae that shoot out from the initial point of nucleation and growth. Any questions about that? All right. And so again, this is also AFM of BAC8, and this is probably a little more representative of terms of how normal polymers behave. You see a bunch of initial polymer crystals shooting out, and then those guys are followed by more polymer crystals shooting out, and then what happens is a subsequent nuclei forms and shoots out from that same location. And then as time goes by, they run into each other, and at some point down the road, we might use this cross-polar cross-polar light to look at the Maltese cross patterns and so forth, but we'd see that boundary there where I just drew that red line. Let's make it a blue line instead. All right, that would be a boundary, a spherulitic boundary that's formed well before anything has filled in all the available spaces. Okay, any questions about that? All right, so this is nucleation growth in situ, which is really nice with these systems. Okay, so we have various laws of structural development, and this brings in a couple of weird little concepts. Crystal thickness and content are dependent on the crystallization temperature. We talked about that last time. Higher temperatures, more energy, fatter crystals, right? And then as we decrease the temperature, then we can start to see thinner crystals develop. The melting point depends on the crystal thickness. Structural changes occur during the recrystallization process. Growth rate is linear dependent on temperature. So this shows us a few things here. This is this concept of easily crystallized units. Easily crystallizable units. And so this is showing you this concentration of these guys at some arbitrary time. And what's happened is we have formed this crystal structure. We have used up all the easily crystallized units. So their concentration has dropped off to 0 in the immediate vicinity of that crystal. And then we have a bunch of them floating around, gradually being attracted to that crystal as it's growing. And so there's a high concentration that kind of falls off with time. But what's happening is they are being delivered to that crystal and starting to crystallize and give you that structure. All right, so just hold on to that thought for a second. We'll talk more about it in a minute. But that's essentially what we're looking at, is polymers that can be easily delivered to a polymer crystal and give you that structure. And we also have this very nice plot, and it shows us a lot of stuff in a very nice plot. So we have stuff that's formed at T0, and so T0 is the lowest supercooling, all right, very close to the melting point. And so we get crystals of a characteristic thickness formed at T0, all right. And so we see that forming, see in this case 4 of those forming, and then we go to a crystallization temperature T1, slightly less than T0, and we get a crystal thickness that's a little thinner than what we saw at T0. And then we go even further, we go to T2, and we get even thinner crystals, all right. So T0 gives us the thickest crystals, T1 is the next thinnest or thickest, and then T2 is the thinnest on this particular plot. And this all has to do with the available thermal energy in these systems. It determines how thick the crystals are, just like what we talked about last time, but all these things are happening in the same structure. All right, any questions about that? Oh my, so far behind all of a sudden. Okay, and so we have structural development. We have a pre-existing crystal face. Epitaxy occurs in that face. Crystallization begins in what's called the mesomorphic layer, and that's what's shown in this little cartoon. We have the crystal that's been forming. It's been able to grow and become thicker, but really all the action's happening out here in front of that growing crystal layer. And so these are polymer chains that are trying to line up and become incorporated, and they do interesting things, like they take a defect that's not going to crystallize, and they can move it up or down to get it out of the way. All right, and so this has to do with this whole concept of easily crystallizable units, meaning that polymer chains that can line up and crystallize. And once they do that, they form this core crystal structure, and that core crystal structure can keep growing. It can grow out and thicken as a function of time. And so that polymer crystal can thicken as this process of hot mobility and perfection is occurring in this mesomorphic layer. All right, and so one way of seeing this is what's called the secondary crystallization process. And again, this is a DSC experiment. And what's happened was they started with branched polyethylene, and they did, if you remember, polyethylene or anything that's in branch form can be difficult to crystallize because it doesn't like to accommodate branches. And so they took this stuff and they did a crystallization experiment where they sat at 115, and then they sat at 100, and then they sat at 75, and then they sat at 25, and then they sat at 25, and stopped, pulled it out, put it in the DSC, heated it up, and what you're seeing here is you see melting at 50, melting at 75, melting a little bit below 100, and melting at 115. And so you're capturing those crystallization events in the DSC experiment. All right, so you force these crappy crystals to crystallize anyway, and then you can see that history in the melting event. And this is an expansion coefficient. Just ignore that for now. We're not going to talk about it here today. And so we have secondary crystallization. Why and where and how does this happen? And this is being shown here in figure 5. So think of, again, what we saw before with the T0 crystals. There's a whole bunch of those in this image. But you have the T0 crystal here as well. And then you can have a T1 crystal that nucleates and grows on T0 at a lower temperature. And then you have the T2 crystal that nucleates and grows on T1 at an even lower temperature. And so what you're looking at here, this is not an arbitrary jumble of figures. This is actually what's occurring inside of a spherulite. The spherulite is finding, nucleating, and growing crystals, and crystals that require a lower temperature to nucleate and grow are showing up epitaxially on other previously nucleated crystals. All right, Nick, I don't have much time for this, so I'm sorry I got behind here. But any quick questions on that? Hopefully that makes some sense. So all has to do with the available thermal energy that is in these systems and what thickness corresponds to those available levels of thermal energy. Okay, and then you force crystallization to occur regardless of the energy, and in doing so, you generate crappy crystals that melt at low temperatures. Okay, so crystallization occurs, but the crystals that form have a lot of defects in them, branches in the case of the polyethylene, or copolymers that don't belong there, but are still incorporated in the crystal structure. Okay, hopefully that makes some sense. Maybe, yes, somewhat. All right, think about it, and I'll have office hours this Thursday, 3 to 5, right? I think that's what it says in the syllabus. And so I'll set up a Zoom call, and if you want to call in, you can. Okay, modulated temperature differential scanning calorimetry. This is a technique that allows us to look at some of these different events. We do have this now, and we actually published a paper last year utilizing this technology. And so we use this because it can separate reversible things such as glass transition and melting, and non-reversible events, what's called cold crystallization, which I actually showed you earlier on, by this constant reversal of heating. And so what happens in this technology is, rather than just continuing to heat up continuously, you heat up and then you cool down, and you heat back up again and you cool down, you heat up again and cool down. And so that allows you to separate out things that are going to be reversible versus these other techniques that are not reversible. And so we'll talk about what that means. Things that are reversing: coefficient of thermal expansion, non-reversing stress release and morphological changes that occur during heating. And the most important one here in this context really has to do with polyethylene terephthalate. Polyethylene terephthalate is a polymer that, as you heat it up, not only does it go through a glass transition, starting from very low temperatures, it also has what's called cold crystallization. And so this is what that looks like. We have this glass transition, which is an endothermic event again, and then we have this crystallization process, which is exothermic, and then we have, again, the endothermic event of the melting that goes on in these systems. And so we see this at the Tg for polyethylene terephthalate, and then at some temperature below melting, we get this spontaneous crystallization event. And then at higher temperatures, those crystals melt. And DSC, or modulated temperature differential scanning calorimetry, comes into place is the fact that if we are looking at the glass transition event, if we start to heat up and go through the glass transition, it is reversible. All right, as we cool back off, it goes back down through Tg again. All right, so that shows up in the reversible scan. We have this crystallization event, which is not reversible. And so if we have the amorphous structure and crystals form, all right, those crystals are there, we cool it off again, the crystals don't go away. All right, they form. There's no reason for them to be reversed as we cool back down. And so that doesn't show up at all in the reversible scan because it's not a reversible phenomenon. In contrast, we do have what's called the non-reversing, which does account for the crystallization of that system. And so what this middle segment that I'm outlining in red here is the combined. And so with modulated temperature differential scanning DSC that's going back and forth, back and forth, back and forth, we can tease out this reversible and separate that from the non-reversible components for PET. Okay? Any questions about that? That's one of the advanced things we can now do with the DSC that we have in the department. All right, so think about this, and we can pick it up from here on Wednesday, and you know, bring any questions you might have. Make sure you understand DSC. Like I said, it's really important that when you see these questions on the test, you know what I'm talking about. Okay? All right, see you guys on Wednesday. This one?
Yes.
Well, this is caused by that crystallization. So it's starting out amorphous, and this crystallization process happens, and it liberates a bunch of heat.
So yeah, there's the glass transition, and then there's crystallization. And
Yeah, yeah, and then there's melting after
which is the big uptick.
the big peak. Right. So you cause crystallization to occur, and then you go to higher temperatures and melt those same crystals.
So first off, you make it. As you heat it, it becomes amorphous. Then it crystallizes. Then
Well, it starts out amorphous, and then it crystallizes.
So what does the glass transition temperature do exactly?
Well, we talked about that last time. It's just taking these polymer chains, and they start to move away from each other.
Okay, I see.
And that's it. That's what TG is. It's amorphous above and below.
Okay.
Okay? Yeah, that's that. Yeah, think about it. Any question?
No.
All right.
Do you know if there's anyone in this room after?
Is there anyone in this room afterwards? I'm not aware of any class.
Yeah, I
Yeah.
checked the matrix. It didn't say.
Yeah, I think there was at the beginning of the semester, but it doesn't seem to be true anymore.
Okay.
Yeah.
I think
Did I what?
Yeah, you passed these back on Friday.
Yeah, I did.
All right.